I can't finish presenting both the two works in last week, so I'll keep like presenting the linear slide in this week's reading group. And before we start, I think in last week when we talked about the parallax angle parameterization and also for Bonner adjustment, I think one thing I don't have time to mention is about after using the parallax angle parameterization, how to calculate the projections at different cameras. For example, the main anchor, associated anchor, and the cameras, or the cameras that other than the two anchors, how to like calculate the projections. Then I think here I give all the equations. It's quite simple. I just use the sine law within this triangle. This triangle, this triangle with the main anchor, associated anchor, and also the feature, right? Then I use sine law to calculate it, and I'm not talking it in too details. So if you're interested, try to derive by yourself about how to do the projections by using the new parameterization. And I think Liang also did a very, very good job on ParallaxBA on the manifolds. Then I think she also has the code released. So if you're interested, you can go to that paper and also the work about how to formulate this on the manifold. And also she proposed a very good linear initialization of ParallaxBA. Then that's a very interesting work as well. So if you're interested, then you can have a look as well. All right, so today I'm mainly talking about the linear SLAM. This work is done, I think, when I first came back to CAS to start just finish my thesis and came back to start my postdoc at CAS. And I should say, at the beginning, Shadun wanted me to prove the number of local minima in the visual SLAM or monocle SLAM problem, because before Shadun had a paper published in RSS, which is about the proof of local minima, the number of local minima in the post-graph case, with just two steps in SLAM. And he wants me to do similar proof in the monocle SLAM or visual SLAM case. But this is more complicated because first it's 3D, and also there's a nonlinear term that if you project the 3D point onto the image. So I spent, I think, almost 3.5 or 4 months to try to prove that, but I can't. Finally, I found. But suddenly I came up to this idea about linear SLAM. So I'll introduce you about that. So in today's reading group, I'll first introduce the idea of linear SLAM, and then we also extend the idea of linear SLAM into the visual SLAM case. So we can apply it to the monocle SLAM and also the stereo case. And at last, I will give some discussions that you may not find them all in the paper. That is something from our experience or our testing experiments, and also from our understanding about linear SLAM and the SLAM problem. All right. So for the linear SLAM, I think all of us know that SLAM problems have been studied for over 25 years, and we know that is a high-dimensional nonlinear estimation or optimization problem, right? So the linear SLAM is based on the idea of map joining. I'll show you a little bit in details about what is map joining. Then, which means linear SLAM is not a traditional way of solving the SLAM problem in either EKF or or like full nonlinear least square problems. But I mean, it's still based on least squares, but it is not a traditional or original like full nonlinear least square SLAM problem. It is based on the map joining, right? And we've shown that a solution to the SLAM problem can be obtained by solving a sequence of linear least square problems, which means we only need to in linear SLAM we only need to solve linear least square problems in the linear SLAM, then which means we don't need to think about the initialization and also the iterations of it, and also local minimum issues, right? Okay, so I think before we introduce the idea of linear SLAM, let me spend some time to introduce what is the idea of the traditional way of the map joining, or we call it the idea of the map joining. If you want to have the map joining ideas in very details, I do refer you to read on Shoudong's TR paper, which is about the sparse local submap joining filter. So this is published in TRO in 2008, and that is a very good paper. And that paper explains the basic ideas about how to do the map joining, right? So in short, by doing the map joining, we are not directly build a whole, or we call it the global map, but instead we use local observations to build local maps first, small local maps first, instead of build a very large global map. And then after the local maps, the sequence of local maps are built, then we try to join those local maps together to get the global map. That's the basic ideas. And the key idea here is that each of the local map is considered as an integrated observation in the map joining. I'll show you about what the integrated observation means in a little bit later. But I mean, the basic idea of map joining is about that. So instead of like building a very large map, so we try to build small maps locally first, and then try to join them together. And there are a lot of ways of doing this map joining. But the ways that we considered, or some others considered, is about like how we can do this kind of map joining by considering that we are not losing any information, original information, and we can maximize the accuracy that we can have during the map joining, right? So I think this is the main work is done in Shoudong's TRO. Then let me show you a very simple example about what the map joining did in the sparse local submap joining filter in Shoudong's TRO paper. All right, so suppose we have this kind of original observations. For example, we only have like three road poses, P0, P1, and P2, and we have three features, F1, F2, and F3. Then at the robot P0, and it observed feature 1 and feature 2. At robot pose P1, it observed feature 1, 2, 3, and at the last pose, then it's the robots observed feature 2 and feature 3. So this is the original observation, and also together with the odometries between the two poses, between the three poses. All right. So, but a traditional way of like, for example, if we do a full nonlinear least square SLAM, then we use all this information, all these observations to build a map, which we defined the P0 as the coordinate frame, which is 0, 0, 0. Then in the map, in the final map, we call the global map. Then we have the pose 1 and pose 2, and also the locations of the three features. right? So this is original way. But in the map joining, we first build two local maps first. For example, we use P1 and P0 and P1, and together with the associated observations, local observations, to build local map 1, and also use the P2 and P3, and together with the related observations to build local map 2. Then in local map 1, we have pose 1 and feature 1 and feature 2, and we use P0 to define the coordinate frame. So which means local map 1 is in the coordinate frame defined by pose 0, and it contains feature 1, feature 2, and pose 1, right? And in local map 2, the map is defined by the starting pose, which is pose 1, and it includes feature 2, feature 3, and pose 2, right? So in this definition, we can see that the end pose of local map 1 is the starting pose of the local map 2. All right, and when you build local map 1 and 2, suppose you build it in least square or in extended or in EKF, then what you can get is the state estimate, the estimate of the state, and together with the information metrics or covariance metrics. If you're using EKF, then you got covariance metrics, and you get inverse, then that's the information metrics. All right, and also the same, you get the the estimate of the state, and also the corresponding information metrics of the local map 2. And by doing map joining, we can see that both the two local maps as the integrated observation. So what I mean by integrated observation is we use both the state, the estimate of state, and the information metrics, right? So in the map joining, we formulate, for example, we formulate it into the nonlinear optimization problem, then which means the state of each local map is the observation, right? So the estimate of the state of each local map is the observation, and we use the corresponding information metrics as the weight, which corresponds to the observation, or as the weight in the optimization problem. Then when we do the map joining of those two local maps, we can formulate the objective function something like this. And this X is the state of the global map, which can be presented here. And in this is the case that the map joining algorithm that used in Shedong's TRO. So which means you build, suppose you have two local maps, and the first local map, it is built, the two local maps are built in the coordinate frame defined by this starting pose. And the end pose of the first local map is the starting pose of the second local map. And the built global map is also defined by its the total starting pose as the reference. And as we can see in this objective function, the first term, which with respect to the first local map, is linear, and the second term, which is respect to the second local map, that is not linear. So solving this map joining problem is not linear. Is that clear for Shedong's TRO paper about map joining? Is that clear? Any questions on that?
So why the second term is nonlinear?
Okay, that is a very good question. So we will also have these things in the linear SLAM. All right. So the first map is the first local map is built in the coordinate frame defined by P0, right? And the global map is also in the coordinate frame defined by P0.
Yep.
Right, so which means the x1 hat is in the coordinate frame defined by P0, and also the capital X, which is the state of the global map, is also like in the coordinate frame of P0. So which means the first term is linear, right? Because they are in the same coordinate frame. But the second one, the second one for x2 hat, the coordinate frame is defined by P1. But for the capital X, which is the state of the global map, is defined by P0. So which means they are not in the same coordinate frame, then which means the second term is nonlinear.
Yep, got it.
Okay, great. I think that's a very good question. We will have these things in the linear SLAM part. Okay, so this is the map joining method. A very brief version of it, because it's only two like local maps. It's a very brief version of the idea that's in the in Shoudong's TRO paper, which is about the map joining. All right, and the map joining method proposed in Shoudong's TRO paper is nonlinear. All right, so I've explained it here. Okay, I think Fred has a question about of defined by two processes. Now, so you can choose any size of the local map. And here I just gave a example, which is a very simple example about like if you're doing it in this way and how you can do the map joining. So you can define the size of the submap. Okay, so I think after I explained it, the map joining, the idea of the map joining in Shoudong's TRO paper, I'd like to ask you a question. So again, we are considering this case. We only have like 3 poses, 3 features. This is the original observations. Then let me ask you a question. Can I build the global map by using the pose 2 to define the coordinate frame? Or can I build the global map that we use pose 1 to define the coordinate frame? Or do we need always choose the first pose to define the coordinate frame of the of each of the map?
I don't think it's really important, no?
Yeah, that's right. So it's not that important, right? You can choose any of the pose to define the coordinate frame, right? Because like in SLAM problems, it's the relationship, the coordinate transformation from the map and also the real world is unobservable, which means we need to define a coordinate frame to your map. And what we always do is to use like the first pose to define it, but you have the flexibility about choosing different poses to define the coordinate frame of your map, right? So here we give some examples. For example, if we start from the same original observation, then we can. What we always do is we can define the first pose as the coordinate frame, or we can define the last pose as the coordinate frame of the map, right? And the second case is, the later case is what we call the robot-centric SLAM. So which means in robot-centric SLAM, it always builds a map that's in the coordinate frame of the current or the latest robot pose. And also we can have the flexibility to choose the other pose within the map to define the coordinate frame, or even we can choose the features to define the map. So that is the B SLAM. I'm not introducing it in very details, but I mean, if you remember, Shoudong mentioned the B SLAM paper which published in IJR in the first talk of this reading group. Then if you're interested, then you can you can have a read on that paper as well. So what that means here that is you have the flexibilities when you build up map. For example, when you use full least square, full nonlinear least square to solve the SLAM problem from the original observations, then you have the flexibility to choose different poses within the map to build up the map. And after you build out map, the maps are equivalent to each other, right? So that's the first thing. And the second thing is, for example, after you build a map here, this map from the original observation and also least square, then if you want to obtain the map defined by pose 2, then you just need to do a coordinate transformation. They are equivalent. They are equivalent. Is everything good here?
Oh, so in the cost function, there was just one term that's linear. The rest are all nonlinear, basically.
For Shoudong's one, yes.
Yeah. Okay.
Only one term is linear. The other rest of them, I mean, if you have multiple maps, the other terms will be nonlinear. Okay, in Shoudong's TRO. And also, why we want to talk about this is I want you to have the idea that you have the flexibility of choosing the different coordinate frames within the map, and the maps are equivalent to each other. And after you get one, then it can be easily transformed to the other one by using a coordinate transformation. And after that, the two maps are equivalent to each other. All right. So this, yeah. Sorry. Any question?
I feel like why picking the initial position as a corner frame is not more accurate. I feel like that because choosing initial position, we know like we actually know the intrinsic like original position of first pose, like that's actually like ground truth. But whatever the rest of generated poses are like noise affected by it.
Yeah, I think that's a very good point. So here we suppose that we don't have any extra information or external information about doing this SLAM. So which means even we have a starting point, we still don't know what's the exact like position in the real world.
Oh, okay. Yeah.
So that's why in SLAM so that is unobservable in SLAM. So that's why we need to find a coordinate frame for the or define a coordinate frame for the SLAM problem. So what we always do is we just consider that is the first pose, which is 0, 0, 0, and then we do that. I think that's a very good point. That's a very good point. So if you define the pose, the coordinate frame of the map as the first pose, then which means the uncertainties which close to the first pose will be small. Will be smaller than the uncertainties which is far away from that pose. For example, in this case, then you can see the uncertainty of feature 1 and pose 1 are smaller than the uncertainty of feature 3 and pose 2. Yeah. Right. Yeah. But in the other way around, if you define the coordinate frame by using pose 2, which is this map, then we will find the uncertainty of feature 2 and feature 3 are small than the others. This is not exactly the case, but I mean, which means in SLAM problem, then the uncertainty will be accumulated. It will be like reduced a lot when you have a like loop closure, but still the uncertainties accumulated, and also the uncertainties will be different when you choose different pose as the coordinate frame.
Makes sense.
Does it mean that somehow, like if you were to pick a pose in the center of your map, or like the pose with the highest connectivity, that would be sort of better? Or no?
I think that's a good question. So I think the authors for the robot-centric, they said why they want to always use the latest pose as the map. as the corner frame of the map is because it in this way it will get a better certainty, and also when it's linearized in EKF, it is better. But what I mean is, suppose you're building this global map from least square problem. The two maps are equivalent to each other. It's just about how you present that map.
That makes sense.
Make sense? Okay, thanks.
I guess. I don't know.
Yeah, we can discuss it a little bit later. I think that's a very good question.
Yeah, sorry, because my question was a yield post. My question basically assumed there's an external frame, but apparently there shouldn't be any external frame. We can't measure anything basically regarding to it.
Yeah. In the traditional SLAM problem, we don't have any external information about it. So in this case, everything is relative. So we need to give a frame for the relative things. So this is why we choose a pose. We choose 3 degree of freedom for 2D case to present the corner frame. Oh, good. Okay, let's keep going. So why I'm introducing this is because this is one of basic ideas that why we can have this linear SLAM. And here is the idea about building and joining 2 local maps in linear SLAM. You can see it's a little bit different, right? So the second map is the same as the second local map is the same as the one in Shoudong's map joining. And the first one is a little bit different. Instead of choosing the first pose as the corner frame, then when we build local map 1, we use the last pose, the end pose, to define the corner frame. That is local map 1. So which means local map 1 is defined, the corner frame of local map 1 is defined by pose 1, and the corner frame of local map 2 is defined by the pose 1 as well. And the joint global map its coordinates is defined by the last pose, which is pose 2. All right, so that is a little bit different from what's in Shoudong's map joining algorithm in his PRO. Then again, so the general idea of map joining is the same. So we use the local maps as integrated observation, and we formulate the map joining like this. And we can see by defining the local map and the global map in this way, both the 2 terms are nonlinear. Both of the 2 terms are nonlinear. They're not linear anymore. But we've proved that joining the 2 maps in this way in the linear SLAM is equivalent to a linear least square plus a nonlinear transformation. This is what we proved in this paper. But I'm not showing you the details about how to prove it. I just want to give you an intuitive way about explaining why it's equivalent to a linear least square plus a nonlinear transformation. So the idea is quite simple. So if we look at this part, right? So the local map 1 is in the coordinate frame of P1, and local map 2 is in the coordinate frame of P1 as well, right? Then we first built, we called it intermediate global map. And we can choose different poses within the global map to define the corner frame, right? So in the intermediate global map, we choose P1 as the corner frame. And it is very interesting that in this case, both the 2 local maps and the global map are in the same corner frame, right? Are in the same corner frame, which is P1, defined by P1. Then joining the 2 local maps to get the intermediate global map is linear. It's just linearly square. It's linear, right? And if you remember, we mentioned that after we get this intermediate map, if we want to have the equivalent map, which is defined by other processes within the map, then we just need a nonlinear coordinate transformation. This is the intuitive way about explaining that why this nonlinear map joining is equivalent to a linearly square plus a nonlinear transformation. Is that clear? Any questions on that?
So everything was regarding to one intermediate pose.
Oh yes, so yes. So what I mean is, if you remember what we introduced here, right?
Yeah.
So we can build map by defining like different poses within the map as the coordinate frame, right? So what we try to do, for example, what we try to do is in the map joining, we first build a map defined by this pose. The coordinate frame defined by this pose. And then we can do a transformation. Then we can get this local map, this global map.
Mm-hmm.
Yeah.
Mm.
Oh, good. Okay, so again, the joining of two local maps in linear SLAM is slightly different. So based on the properties that we use, that the maps can be built in different coordinate frames. A different coordinate frame defined by different poses within the map. Then the first local map and the second local map are both built in P1. And the joint local map we want to have is defined, the coordinate frame is defined by P2, right? And an intuitive way to showing why this nonlinear map joining is equivalent to linearly square plus nonlinear transformation is we first build an intermediate map, so which is also defined by P1. So which means when doing the map joining, you have local map 1, local map 2, and the global map. They are all in the same coordinate frame. Then which means during the map joining, it is linear. And then after you get the intermediate map, intermediate global map, then you can do a coordinate transformation to obtain the map which the coordinate frame is defined by P2. That is intuitive way about like explaining about this idea of linear SLAM.
So like, do we do every single step? Like every single step we cluster P1 together, push to the next P2?
Yeah, that's a, so what do you mean by a single step?
Like we do like every single step. So if we have P3 now, we cluster P2 together, push to P3.
Oh yeah, that's a very good point. That's a very good point. This is what I'm going to show you. So if we have like multiple or a sequence of local maps, how we can do it. And in this case, we can do we can join all the local maps either sequentially or in a divide conquer manner. The sequential mean is you always join the latest map with your current global map, right? And a divide conquer means every time you join two of the local maps and you have different levels of the maps, and then finally you joined the maps together. I mean, both of the two methods, either sequentially or in divide conquer manner, we try to join two local maps or two maps at each time, because linear SLAM can only be linear when joining two local maps. I think Josh has a very good point on this. So when you have multiple maps, what we are trying to do in linear SLAM is every time we just join two local maps, and then we have like different steps about joining the sequence of local maps together with the global map. But each time we only join two local maps. then we can make every step linear. All right, and if you're doing similar things about the map joining or something, then I do suggest you to do the divide and conquer case. Divide and conquer case. All right, so we tried both sequential and divide and conquer. First, sequential, if you have multiple numbers, I mean, maybe a large number of local maps, a sequential case will take longer time than the divide and conquer one, because because divide and conquer solve it in a hierarchical manner, then it joins less time, and do the map joining less time than the sequential one. And also we found that the result we got from divide and conquer, the accuracy is slightly better than the sequential one. So if you're doing map joining, I do suggest you to do a divide and conquer one instead of sequential. So what I mean is, the linear SLAM can only be linear when joining two local maps. And if you have multiple local maps, then what we can do is we can do a map joining on either sequentially or in a divide and conquer manner. Then we can make sure that at each step, at each time, we only join two local maps. Then we can obtain the global map. All right, so that is the basic idea about linear SLAM. So what I want to say here is the linear SLAM is a unified linear approach. So which means it can solve the feature-based SLAM and post-graph SLAM, and also the D-SLAM Zhao mentioned in the first talk, which is it only has features without any poses, and it can solve the SLAM problems in both 2D and 3D manner. And also it does not need any requirement on the structure of the coherence matrices. If you find any other like works about feature-based SLAM or post-graph SLAM, they may need some like spherical assumption on the coherence matrix, but here we don't need that. And there's no need of initial guess in the map joining, and there's no iterations. We only solve at different steps, but in each step we don't have any iterations because it's linear. All right, and here are some examples. So here are some like examples about the experimental results. And this is the case. These are the results for the feature-based SLAM case. And we show 2D case. We use Victoria Park and DLR datasets, very old datasets. And for the two results are like the map joining of 200 local maps, which is the dataset we got from the code Shoudong released on OpenSLAM together with the sparse local submap joining filter algorithm, right? And the second two, Victoria Park 6898 and DLR 32998, they are the results that we consider every single pose as a local map. So which means we don't need to build a local map. We just simply consider each of the pose together with the feature observations as one local map. So which means when we use these two data sets, we don't have any nonlinear part involved. And here are the results. And this is a 3D case, a 3D feature-based case. We use a simulation. And from the results, we can see that the linear SLAM result is better, is always better than Shoudong's one, than Shoudong's TRL one. And it is very, very close to the full nonlinear least square result. So which means it is very close. It is very close to the full nonlinear least square SLAM, and also because at each step we solve the linear least square problem, which means we always have the optimal solution at each step. So in this case, it will be better than Shoudong's sparse local sum adjoint filter. All right. Then we also have some results on the post-graph one. So if we have like three 2D data sets, Intel, Manhattan, and City 10,000. And we also have 2 3D data sets, which is Sapphire and also Parking Garage data sets. As we can see, it is quite close to the 4 nonlinear least square SLAM results, and it's better than HOG-Man. I think I compared some other algorithm, but I didn't show you here. And here's also some results for the DSLAM. I'm not going to introduce it in very detailed, but I mean, if you're interested in about what is DSLAM, then please refer to Shoudong's IJR paper, another IJR paper. And in short is in DSLAM, we don't have any poses. We only have features in the map. Okay, so this work has been published in IROS in 2013, and the journal version has been published in Automatica, and we also released the source code on OpenSLAM. So if you are interested in this work, please refer to the journal version of the paper and also the code. So we have MATLAB code. We also have the C++ code if you want. All right. So after we introduce the linear SLAM, I'll give some conclusions on that. So the properties of linear SLAM is as what we mentioned, because it's linear, we don't need any initial guess. We don't need any initial guess, and there's no iterations. Right, so both of the 2 properties are very important in visual SLAM or molecular SLAM, because in molecular SLAM or visual SLAM, we always need a very good initial guess in case it cannot be converged, right? And also, we always have a lot of iterations at each step of the visual SLAM. And we also mentioned that linear SLAM is a unified linear approach. It can solve like feature-based SLAM, post-graph SLAM, and DSLAM in 2D and 3D case. But our question is, can we use this idea in the molecular SLAM case or visual SLAM case? And the answer is yes. The answer is yes. And the difference is it is a bearing only. As what we mentioned in the ParallaxBA, it's a bearing only observation, and we cannot observe the scale. So there's no scale. So we need to consider those things in the linear molecular SLAM or linear SLAM motion or linear visual SLAM case. So based on the idea of linear SLAM, we propose the linear molecular SLAM. The idea is quite similar. It's quite similar, but what I want to mention here is when you do visual SLAM or molecular SLAM, or you do a Bond adjustment, you need to fix 7-degree freedom in case there's to avoid the singularity of the information metrics. Can anyone tell me why? And what are they?
Oh, so for ParallaxBA?
Yep.
I think it was XYZ and anchor and parallax angle. And
yeah. So in all the visual SLAM or we call it Bond adjustment problem, because everything is relative. Again, it's relative. We don't have GPS on it or something. Then we need to fix a coordinate frame. It is similar to what we mentioned in the feature-based SLAM problem as well, right? So we need to fix a pose as the frame, as the coordinate frame of the map. Then what we always do is we choose a pose. We choose a camera pose and fix it as 0, 0, 0. Then that's the coordinate frame. And normally for molecular SLAM, it is 3D case, right? And for a pose, it's 6-degree freedom, 3 for XYZ and 3 for rotation. then which means we need to first fix 6-degree freedom, which means we fix one pose. And another thing is about scale issue. It's about scale issue I mentioned here. So in the molecular SLAM, we don't have the real scale. We cannot have the real scale without any external information. For example, when you do a molecular SLAM, you can build a map, but the complete map is up to 1 scale to the real world. Is that clear? Yeah, for example, if you're doing if you're running off SLAM 2, without any external information, you get 2 points of your table in your map. And then in the map, it tells you that this distance is about 10 centimeters. But in the real case, your table is about 100 centimeters. All right, so that is up to 1 scale. But the thing is, when you do the map, when you do the molecular SLAM, everything is in that scale. So which means your robot poses, sorry, your camera poses and your map are up to 1 scale to the real world, but everything is in the same scale, right? And what we always do, suppose we are in the boundary adjustment. So what we always do is we fix a translation of the second pose as the scale, then to make the information matrix not singular. For example, in this case, suppose we have 3 images and we observe 3 features again, but we cannot solve it in this case, but I mean, just an example. Then what we always do when we do the boundary adjustment is we first fix the first pose as 0, 0, 0, 0, 0, 0 as the corner frame. And then we choose the largest transformation element from pose 1 to pose 2 and make it equal to 1 as constant and fix it as the scale of this map. For example, in the normal case, that the z value of the second pose P2 is the largest one among x, y, z in the pose. Then we choose the z value of the second pose as 1 and fix it as the scale. This is what we always do when we do map draw. Sorry, when we do when we solve molecular SLAM problem. All right. Then again, by using the properties we have before, we can build another map based on the same orientation observation. So which means we can choose the second pose as 6, 0, as 0, 0, 0, 0, 0, 0, which defines the corner frame. And we can choose the translation on the z-axis of pose 3 as equal to 1 and as the scale of this map. Then we can get another map, right? Another map. And as what we mentioned before, the 2 maps are equivalent to each other. And after you get 1 map, you can transfer it easily to the other map by using a nonlinear coordinate and scale transformation. Right, so that is a little bit different. I mean, the basic idea is the same as the linear SLAM, but when you build local maps, when you transform the local maps, it's a little bit different because we have a scale. We need to consider the scale as well. All right, so after we have this property, then we can define our linear molecular SLAM. And in the linear molecular SLAM, we build the initial local map by every 3 poses or every 3 images, not 2, every 3 images. That is the initial one, and we build the initial local map by using boundary adjustment. And when we choose the local maps, at the 2 nearest local maps, we have two common poses, or we have two common images. And why we are doing that is because we need to also transform the scale. All right, and after we defined the initial like local maps by using every three images built by boundary adjustment, then we can join every two initial maps into one map. It's similar as what we had before. It's linear. Then you can also transform the corner frame and the scale into other definitions a little bit later. And again, similar, joining a sequence of initial submaps or initial local maps can be done in a divide and conquer manner. So which means at each time we only join two local maps, then at last we will have our global map. So the idea is quite similar, but it's just need to deal with the scale as well. So that's why we need to have like three images in the initial local map, at least three images in the initial local map. And between the two maps, we need to have like two common images or two common poses. All right, and because we only like build the local map with three images, then we build it in the boundary adjustment. It's very easy to initialize and it's very easy to converge. So it's super easy to get the initial local maps with three images. And after that, everything is linear. Sorry, everything is linear. All right. And here are some, I think I don't have too much time, then here are some results. And this one is the Malaga parking data set. Then we have 500 poses, we have around 200,000 features, then we have around like 500 projections. Then we built every three images as initial local maps. Then we have like around 506 initial local maps, and we join them together. Then we can have the global map. And here, this one is the result of the Malaga the campus dataset. Then we have 1,020 poses. Then we have around 200,000 features and around like 600,000 projections. Then we built like around 1,018 initial local maps, and we join them together. Then we have the global map. And this is the result of village dataset. This one is the photogrammetry dataset, and here we also have the college dataset. So in this case, we have like around 500 poses and around 400,000 features, and we have like 1.3 million projections. And here I want to show you a brief video about how this divide and conquer process about linear MonoSLAM works. So this is the campus dataset. And we can see like initially we have more than 1,000 local maps, then we join them together. Every time it's two local maps together, then we have the global map at last. And this one is the college dataset, which we have around 500 images. Then initially we have nearly 500 initial local maps. Then we join them together to have the global one. And here are the accuracies we have. Then we can see that it's very close to the boundary adjustment, which is the ideal, like the gold standard, which means we can get the best result we can get. And it's quite close to that. And for the computational cost, for the college dataset, we have around 100 seconds, and for the village dataset, we have like 42 seconds, something like that. Then this work has been published in ICRA 2014, and the journal version has been published in SPIS journal Photogrammetry and Remote Sensing. And we also have the code published available. And I don't think I have too much time now. I have a lot of discussions, but don't have time to discuss. One thing I want to say is here is a result of a stereo case. Stereo case. I use the Oxford New College dataset. I think most of you are familiar with it. It's a stereo case, but I mean in stereo it's very easy because it's stereo. Then we build the initial submap by every 2 images because it's stereo. We can observe the scale. Then we don't need like every 3 images and with 2 poses, with 2 common poses. So we can do a normal one. So which means we build the initial map with only every 2 images and with one common pose to the other initial local map. And then it has like 3,500 poses and around like 500,000 features. Then this is what we get. It's quite close to the full boundary adjustment result. All right, and that is mainly all for today. I may not have time to do the discussion. Then if you have questions, then we can discuss based on that. Thank you very much. Any questions?
Thanks, Liang. Yeah, I do have a question. Like for divide and conquer, like you do it with respect to time, I suppose.
Yeah.
Would there be a way to do it with respect to space? And would there be an interest in doing so?
By saying space, you mean the memory or something?
No, like in terms of, well, I guess it might be much harder computationally, and maybe there is no point in doing so. But like, you know, doing something where like instead of joining it with time, like you join them with like, you know, by feature matching, like with like finding which one are close to each other.
Yeah, I think that's a good point. So currently in my work is we suppose that the images or the local maps are in order. So which means we know which one is next to each other. But I mean, I do have another work. It's not published. I do have another work we submit to a conference before, but haven't published. That is if we have images or if we have local maps without order. And that in this case, I think it's better to have a tree connectivity one, to have the connectivity first. And then we can organize like which part to at each time, which 2 submaps can be joined together, something like this. I think that's a very good point. Yeah.
Yes, because so for example, if you have 2 different data collection that you want to merge together, then you cannot do it with time, right? Like you have to do it with time.
Yeah, that's the thing. That's the thing. We didn't consider that. I mean, that is something we should consider in the real case. Yeah.
Yes. Thanks.
Thanks, Raphael. Any other questions?
Liang, I have a quick question. Rick, when you, in the monocular case of the linear SLAM, when you fix the scale, I mean, I can see how it will work for if the camera is moving roughly at the same velocity.
Yeah, that's a very good point. I have the discussion. I don't have a chance to show it. I have the discussion. So currently we are thinking, where is it? Wait a minute. I have discussion. Whatever. All right. So what I mean is, currently we are supposing that we don't have like 0 translation for the 2 first poses or between the last 2 poses. But the thing is, we can easily deal with that by including more images into the initial local map. So it only requires that the translation between the first 2 poses and the last 2 poses are not with 0 translation. So which means if you have like the camera not moving,
okay, so you mean that they share both poses, you mean?
Yes, so suppose currently you have like your camera stationary at the moment, right? Then you can keep more images within your initial map. And then when the camera moves, you can stop like building that that initial local map.
Yeah.
Yeah, and which means what we only need is if the first two poses. Sorry, taking time. Yeah. So what we need is if the first two poses and the last two, sorry, the poses between the first two and the last two, they are not with zero translation, then that's fine. Because we only, when during the map joining, and we only need to consider the case that we fix the scale with the first two poses or the last two poses. So if you have like multiple images, multiple poses in the middle, but with the stationary case, then it should be fine. And in our experiments in using the Malaga datasets, there are some cases that the camera like just slightly moved. It's not like exactly stationary, but just slightly moved. So we have a case that the car like stopped when giving ways to the other vehicle and then move again. In this case, it doesn't affect the result. So which means it's like theoretically like 100% stationary, then we can include more images within the initial map. But I mean, if it's have slightly moved, it shouldn't be an issue in the case.
Yeah, cool. Thanks.
Maybe for Raphael's question, if we have two submaps built at a different time step, but they have common features or overlaps, we can still use linear SLAM to fuse them together. The only difference is we need to somehow to get the data association we know which features are the same and the relation between the two submaps. I don't think we really need all the maps need to be in sequence in time. That's my understanding.
Yeah. I think you just need to find one place where they overlap.
Yeah.
And you can use it as a bridge to link all of them together, I suppose.
Yeah. Actually, we did it in that way in DSLAM, and also we did it in that way in the MonoSLAM case. And we submit paper to ECCB, we didn't get accepted, and we just leave the work there.
Wow, unfortunate.
Liang, and what if you have like if the connectivity is more than one, so you have multiple poses connected? Does that affect something? I mean, with the loop closure.
Different connectivities to join, right? Is that what you mean?
Yeah. More than one connectivity.
Yeah. I think in the we didn't like consider too much on that in this case, but it seems like it doesn't affect. If we didn't like choose the joining of the two maps carefully, but it seems like it doesn't affect too much on the work. And one example in this case is when you have like sorry, wait a minute. So when you have the post graph case, and in this case I use every single pose as one local map, and we start, which means we don't need any like nonlinear case in it. But you know, there are some like loop closure relative poses between them, right? So we didn't carefully choose which two local maps to join together. So I just joined it like sequentially. I mean, we just order it sequentially and in its nature order, and then we join them together. Then it doesn't affect the result.
Yeah, cool. Thanks.
Thanks, Teresa. Any other questions?
I have a rookie question here. At the scale.
Yeah.
Like, what is actually like? What's scaling here? What's being scaled here?
Yeah, I think in MonoSLAM, in normal SLAM, we need to fix one pose to define the coordinate frame of the map. So that is okay for you, right?
Yeah.
Okay, okay. And in the MonoSLAM case, we also need to fix a pose as the corner frame. So that is okay as well, right?
Yeah, yeah.
It's only about things about scale. Okay, so that's a very good question. So suppose you have an image. How can I say? Suppose you have an image. You have an image here, and then you have an image here, right?
Yeah.
And what you have in the multiple case is you only have bearing only observation.
Yeah.
So which means you have the UV which representing this direction, you have UV which representing that direction.
Yeah.
Right? Right. And we can do a triangulation and to get, suppose we can do a triangulation to get this point.
Yeah.
Right. But the distance or the depth is with respect to the scale of the distance between the two images or the two cameras. Is that right? But the thing is, you don't know the exact scale of this distance or add this distance, right?
Right.
Which means we can build a map from MonoSLAM, but it is up to one scale to the real world.
Oh.
And when we solve the boundary adjustment problem or MonoSLAM problem, we need to manually fixed a scale between them, and then you can solve it without any singularity. And we always choose the largest element of this translation. For example, when your camera is moving forward, that is Z. That is Z. Then we choose the Z element of this relative translation equal to 1 as the scale. Then you can solve it without any singularities.
Okay. Okay, got it.
All right, cool. Any other questions? Any other questions? All right, so I think if there's no questions, I will thank you guys again for your for attention, also for your interest in my previous work. Thanks a lot. And if you have any questions about the paper, about the code, and also something behind that, so feel free to contact me. All right, thank you very much.
Thanks, Liang.
Thanks, Liang.
Thank you.